Good afternoon. My name is Scott Lanning, and I'm here to present to you on my airplane configuration optimization tool. In the aerospace industry, there's kind of a well-known joke what each group would wind up with a final airplane product if they had complete design autonomy, right? The fuselage group in the top left-hand team would have basically all seats, probably not an airplane. The engine group would basically have a flying engine with little tiny stub wings. And the stress group, which I'm particularly proud of at the Boeing company right now, would have very rigid structure, heavily redundant joints and gaps, and probably not get a lot of economy and or money out of the system. So in reality, a lot of these trades are blended together, parameterized, and kind of traded with one another to come up with optimal solutions. This project will look to explore a similar idea with relating most of these parameters to the cost function and helping optimize off of that. So shown here is a family suite of airplanes from large to small. You can understand how the range would be impacted, as well as obviously passenger volume and therefore revenue brought in. Just kind of another example of how all these trades are brought across and understood. Walking through some of the preliminary parameters that have been identified, the cost function again will be the objective function trying to be maximized, plane revenues minus plane costs. Plane drag related to not only the volume, but the thrust force required is directly related to fuel burn, which has an associated cost. The volume, again, how many passengers can be on board relates to the revenue on board, but that also relates to the drag cost. The time of flight can be related to ticket prices, but that also relates to fuel burn and drag profile. And there's also range considerations as well. So some baseline assumptions are going to have to be made to help kind of contain our design space. Some of the which that have been kind of laid out here are the drag profile shown in the blue highlight, how big the aircraft is trying to get through the air. That pertains to how much gas, luggage, and people you can have on board. Looking here at an example design space, a drag profile is shown. The top check kind of profile represents the summation of the two drag curves. Here's a potential volume constraint, right? Increasing volume is going to increase your drag. Increasing the flight airspeed, it decreases your flight time. Here's a potential fuel volume constraint parameter, right? And we can now see that we wind up with a design space and a couple optimal points for checking. Note that these are approximations. This project will aim to explore what happens if we manipulate some of these parameters and design spaces and what we can come up with as a final solution. Using graphical and numerical optimization methods and nonlinear program solvers, we believe that we can find an optimal airplane design based on user inputs. Here's some sources cited. Thank you.